Welcome to our first screencast from Module 5, Lesson 1. I'm actually on page 194, which is the sheet before the actual start of the lesson. And there's some information there that's helpful, so I wanted to point it out. You guys have done linear equations before. You've done lines, and dealt with slope and y-intercept and things like that, some in 8th grade, but we're going to expand on it obviously now. But this is a good reminder, so you might want to put a bubble, highlight it, whatever. And I'm actually going to clean it up just a tad. The slope is positive if the line slants up. Well, they mean if it slants like up and to the right. Slope is negative if the line slants down and to the right. If you have a line that's horizontal, the slope is 0. If you have a line that's vertical, the slope is undefined. So those are some things that you've learned, but I wanted to point them out because you may have forgotten them. Okay, so I highlighted those, and then I added, slants up and to the right, slants down and to the right, that kind of thing. Also, you will notice sometimes I will put a little triangle for shorthand. That means the words change in. So for instance, when you have calculated slope before, it's basically rise over run, which means your change in your y values divided by your change in your x values. Okay, so this is the way to calculate slope. Looking at these down here, they did this one for you. This one, the slope is negative because it slants down and to the right. If I wanted to take a look at this, I could go, that's 5 boxes down, so a -5 is my change in y values, and then 5 boxes to the right is my change in x values. So -5 divided by 5, my slope is -1. Here, this is a horizontal line, and remember, on a horizontal line, the slope is 0. So just some reminders. You've seen this before, but it's been a while. All right, join me on page 195 and let's get started. So our goal for this lesson is to understand linear functions. You've seen them before. We may not have named them linear functions. I don't know. But what is a linear function? It's a function. Remember, a function passes that vertical line test. It's a set of ordered pairs that when you do the vertical line test, it'll not hit that graph more than one time. But a linear function is a function that creates a straight line when you put it on a graph. Okay? All right, so for instance, let's just dive in. It says a race car can travel up to 210 miles an hour. If the car could travel continuously at this speed, then y equals 210x gives the number of miles, y, that the car would travel in x hours. Solutions are shown on the graph below. Okay, so after 1 hour, they would have gone 210 miles, 420 miles, after 3 hours, 630, etc. Okay, so the graph of the car's speed is a function because every x value is paired with exactly one y value, and because the graph is a non-vertical straight line, it is a linear function. Okay. Now it says to fill in the table using the data points from the graph. So we're going to take these and we're going to put them in the table. And I've already done this for you. So down here, my x values, my times in hours, 1 hour, 2 hours, 3, 4, 5 hours. My y values are the distance that that car has gone. So after 1 hour, it's gone 210, and then 420, and then 630, 840, 1050. Okay? So we filled in the table. That's part A. And then part B says, using the table, check that x has a constant change between consecutive terms. Yeah, from 1 to 2, that's a change of 1. From 2 to 3, that's a change of 1. From 3 to 4, that's a change of 1. From 4 to 5, that's a change of 1. Great. The next one on the next page, over here, right there, C on the next page actually says, now check that y has a constant change between consecutive terms. Okay, so from this y value to this next y value, that's a change of 210. From 420 to 630, that's a change of 210. From 630 to 840, that's a change of 210. From 840 to 1050, that's a change of 210. So, constant change of x values, constant change of y values. Okay? All right, so we already did this on the previous page. Using the answers from before on B and C, what change in x corresponds to a change in y? Okay, so we went up by 1 for our changes in x. We went up by 210 for our changes in y. So our change in y over our change in x is 210 divided by 1. Okay, that's rise over run. That's your calculating slope there. All right, all linear functions behave similarly to the one in this example. Based on this information, a generalization can be made that a constant change in x will correspond to a constant change in y. In other words, that means that the slope for the line is going to stay the same anywhere along the line. Okay, so going back, I know they didn't connect the points and they could have, but if I take this section and calculate the slope, I'm going to get the same slope as if I took this section to calculate the slope of the line, because the slope of the line doesn't change. It doesn't change because it's a linear function, meaning it makes a straight line. Will a nonlinear function have a constant change in x that corresponds to a constant change in y? No. Okay, we're going to show you the difference down here at the bottom. Number 2 says that y is equal to x squared. That actually represents a typical nonlinear function. You're going to learn later on next semester that that is a quadratic function. You don't need to know that right now, but it's another type of function. But it's not linear because the line it creates is not a straight line. Okay, using the table of values, check whether a constant change in x corresponds to a constant change in y. Well, 1 to 2 to 3 to 4 to 5, I'm changing by 1 each time for my x values. But over here on my y values, when I put in 1 into this equation, 1 squared is 1. But when I put in 2, 2 squared is 4. So a change from here to here was a change of 3. But then I do it again. 3 squared is 9. Well, the change from here to here is a change of 5. And change from here to here is 7, etc. So there's not a constant change over here on the y values. Okay? And like I said, this function, this graph is a function, okay? But it's just not a linear function, okay? Because it's going to do this. Like down here, if you took the slope of the line, it would be maybe like this. This point, the slope's a little steeper. This point, the slope's even steeper. So the slope does change because the line's curved. All right, on 197, where it says proving linear functions grow by equal differences over equal intervals, I'm not actually too worried about you running through this and understanding, because it looks like a whole lot of letters and symbols and things, and it may be kind of intimidating looking. So I'm not super worried about that. But the point of this is that they're trying to make that, you know what, the change in x values, whether I take it from x2 to x1 or from x4 to x3, whatever, the change from one to the next is always constant if it's a linear function. One of the key things that I do want you to highlight is this reminder. It's also important to know that any linear function can be written in the form f of x is equal to mx plus b, where m and b are constants. Okay? You might have seen it as y equals mx plus b. You're going to find out soon that m is your slope, so the slope of the line, and that b is your y-intercept, meaning where the line crosses the y-axis. Okay, I'm not super worried about any of this. All right, go down to number 3. Consider the function y is equal to x to the third. Use 2 equal intervals to determine if the function is linear. The table for y is equal to x to the third is shown. Okay. So my x's have equal intervals, a change of 1 each time. But my y's, so that's a change of 7. That's a change of, like, I don't know, 19. Okay, so these changes from one y value to the next y value is not constant. That tells you that this is not a linear function. Now, it is a function because each x value generates one y value. Okay, it's a function, but it's probably one of those curvy functions. Okay.